This aircraft weighs 220 tons. And it has less than 10 minutes to get airborne. Physics says, that's a problem. 220 tons of aluminum, fuel, and weapons. 8 turbojet engines designed in the 1950s. A wingspan wider than many modern airliners. And a runway that may not be there tomorrow. Visual, archival footage of a Cold War-era bomber sitting at the end of a runway. Cut to a stopwatch counting down from 10 o'clock. During the Cold War, the mission was simple. If nuclear war begins, you have minutes to get airborne before the runway disappears. No second attempt. No margin for error. So here's the engineering question. Can a 220-ton aircraft like the B-52 Stratofortress actually take off in under 10 minutes, reliably, and why does physics make that so difficult? Today, we're not looking at marketing claims. We're looking at lift equations, thrust-to-weight ratios, and why this design shouldn't work, yet somehow still does. The B-52 wasn't built for elegance. It was built for deterrence. In the 1950s, the United States needed a bomber that could carry heavy nuclear payloads, fly intercontinental distances, survive long enough to matter. Unlike modern stealth aircraft like the B-2 Spirit, the B-52's survival strategy wasn't invisibility. It was altitude, range, and sheer numbers. But there was a problem. Runways are fixed targets. In a first strike scenario, the time between detection and impact might be less than 30 minutes. That means aircraft must start engines, taxi, accelerate, reach rotation speed, climb away, all before the runway becomes unusable. 10 minutes isn't arbitrary. It's the window between warning and destruction. And physics doesn't care about urgency. Let's start from first principles. An aircraft lifts off when? Lift \check weight. Lift is defined by L equals \frat 1, 2 \rho v squared sc underscore L. Where rho equals air density, v equals velocity, s equals wing area, c equals lift coefficient. Weight, meanwhile, scales directly with mass. At 220 tons, roughly 220,000 kilograms, the gravitational force is about 2.16 text million newtons. That means the wings must generate more than 2 million newtons of lift before rotation. So how do you increase lift? You have only 4 variables. Increase air density, impossible. Increase wing area, structural penalty. Increase lift coefficient, stall risk. Increase velocity, requires runway length and thrust. Everything points back to speed. And speed requires thrust. The B-52 uses 8 engines because in the early jet age, individual turbojets were weak and inefficient. Visual, exploded diagram of early turbojet engine showing compressor, combustion chamber, turbine. Early engines like the Pratt & Whitney J57 produced around 10,000 to 13,000 pounds of thrust each. 8 engines multiplied that into something usable. But here's the catch. Thrust-to-weight ratio determines acceleration. If thrust barely exceeds rolling resistance and drag, acceleration is slow. Acceleration determines runway distance. And runway distance determines survivability. The B-52's solution? More engines. Not for speed, but for redundancy and acceleration. It's brute force engineering. The engines get attention. But the wing does the real work. The B-52 has an enormous, high aspect ratio wing. High aspect ratio means long and narrow, similar to a glider. Why? Because induced drag decreases as aspect ratio increases. Visual, CFD simulation comparing short stubby wing versus long slender wing. Induced drag is the penalty for generating lift. It's strongest at low speeds, exactly during takeoff. So to reduce takeoff distance, you increase wing area, you increase aspect ratio, you reduce induced drag. But that creates another issue. Long wings bend. At takeoff weight, B-52 wings flex dramatically upward. Visual, slow motion footage of B-52 wing flexing during rotation. This isn't a flaw. It's deliberate. Flexing reduces stress